Hi everyone, I'm Yuhao Liu from Fudan University. Today I'm honored to talk about our work, Regularizing Sparse and Imbalanced Communications for Voxel-based Brain Simulations on Supercomputers. Brain simulation is the concept of creating a functioning model of a brain or part of a brain. It facilitates the understanding about how a brain perceives, thinks, and acts in a scientific way, and forms an important part of cognitive computing that has both scientific significance and a broad variety of practical applications. However, the connections of neurons in biological brain present a sparse and unbalanced communication pattern, which does not match the highly structured network of supercomputers and seriously affects the communication efficiency. The goal is to reduce the communication latency of large-scale brain simulations, increase the simulation speed, and lay the foundation for neuroscientists to explore the mysteries of the brain. A high-level procedure of brain modeling of simulation is illustrated in this slide. The procedure starts with constructing a digital brain model based on the multimodality MRI data obtained from real human brain. The brain is modeled as a network of interconnected voxels, each of which simulates a set of neurons, where the voxel sizes, connectivity, and activity of the brain is measured through MRI data. With a predefined simulation scale, the number of neurons simulated by each voxel is proportional to the voxel size. The connections among voxels, modeled by DTI, is a sparse matrix, in which each non-zero element represents the normalized probability that synapses are formed between the neurons in the corresponding pair of voxels. Voxels are further divided into neurons, and synapses are formed between neurons to form a brain-level spiking neural network. With the precision of existing MRI equipment, the number of voxels in the human brain is several times the number of processors available in the supercomputer, so we need to partition the voxels into individual processes to map the brain model to the cluster. When the simulation begins, it mainly includes two parts. Firstly, computation that simulates neural activities executed by a set of processes and accelerated by GPUs. Secondly, communication among processes that simulates information exchange between neurons through message passing. The computational part can be well accelerated by GPU and vectorized algorithms. The hardware performance have been fully exploited in our platform. When the scale of simulated neurons increases, the computational speed will not be the main factor restricting the efficiency of the simulation. However, due to the imbalanced communication pattern in the human brain, the communication overhead will become the most important factor limiting the simulation speed. These two figures show the sparsity and irregularity of communication in the human brain. The figure on the left shows the message count and traffic volume of each process when simulating with 1,600 processes under the point-to-point communication strategy, where the straight horizontal line shows the maximum value, while the dashed line gives the average value. It clearly shows that only a small portion of processes generate a large number of messages or heavy traffic, while the majority of processes send out much fewer messages or lighter traffic. Since the brain simulation is performed iteratively, and the speed of each iteration depends on the slowest process, the few extreme values, which are much larger than the average, become stragglers that slow down the entire system. The figure on the right shows the message count and traffic volume of each process when process scale is 10,000. Each process needs to communicate with about 200 other processes on average, and the process with the largest number of messages needs to communicate with about 3,000 other processes, which is 15 times the average. The comparison indicates that the sparsity and imbalance will become more severe as the simulation scale increases, which indicates that only a well-designed communication mechanism is needed for balancing the traffic and improving communication performance. The mismatch between the communication patterns in brain models and the highly structured communication system in supercomputers severely limits the performance of brain simulations. So, we implement a virtual communication topology, or the VCT, that exploits the sparsity to balance the irregular communication loads and shorten latency for brain simulations. The proposed virtual communication topology works on the software level and is oblivious to the underlying network architecture and network devices. Suppose the simulation runs on capital N processes denoted with P and use message passing for inter-process communication. The virtual communication topology organizes capital N processes into a regular n-dimensional structure, Tn, where k is the length of each dimension and the multiplication of k is equal to capital N. In the VCT, each process is uniquely identified by a coordinate, and two processes whose coordinates differ in only one dimension are defined as neighbor processes. Communication between processes is divided into n stages. Only processes that are neighbors on the dth dimension can send messages to each other on stage D. For processes pair that are neighbors in the dth dimension, messages between them will be sent in a point-to-point manner on the dth stage. In contrary, the messages exchanged between processes whose coordinates differ in more than one dimension will be forwarded by neighbor processes before reaching their destinations. After organizing the point-to-point communication like this, the message count will be reduced from order capital N to order n times nth root of capital N. Let's take a 2D virtual communication topology as an example to explain how VCT works. Suppose process A needs to send messages to process C, D, E, F, G, and H. Without the proposed VCT, process A will send a message directly to each target process via point-to-point communications. With the proposed two-dimensional VCT, inter-process communication will take place in two separate stages. In the first stage, messages can only be sent between neighbor processes on the first dimension. Therefore, process A sends a message to process C and D, respectively, in the first stage. The messages from process A to process E, G, and H will be sent to the first-dimensional neighbor processes of process A on the first stage, and then are forwarded by the relay processes to their destination on the second stage. The message MAG is sent to process B first, and then forwarded by process B to process G on the second stage. Although there is no information exchange between process A and process B, because process B needs to undertake the forwarding task, process A still has to send a message to process B in stage 1. This figure presents a three-dimensional VCT to further explain how does the VCT works in higher dimension. Similar to the two-dimensional topology just mentioned, the three-dimensional communication topology divides the communication into three separate stages. The shades of yellow, blue, and orange represent the neighbors of the process of coordinates 1, 1, 1. Messages between those processes differ in more than one-dimensional coordinate need to be relayed by neighbor processes. Forwarding in the dth stage sends the messages to neighbor processes whose coordinates in the dth dimension are the same as the destination processes. Although the total traffic volume could increase in the virtual communication topology comparing to direct point-to-point communication due to multi-stage message relay, exploiting the homology of spikes allows us to dramatically mitigate the increment in traffic volume. Homology of spikes means that the spikes fired by the same source neuron are exactly the same, regardless of their destination neurons. This means we can merge the spikes from the same source neuron, encapsulate them into one single message to reduce duplicate copies, which greatly reduces the increase in traffic caused by message forwarding. The sparsity of communication is well exploited through the aforementioned VCT. However, if the voxels are not effectively partitioned to the processes, the imbalance of communication load would significantly slow down the entire system. Therefore, An effective partition algorithm with traffic balance taken into consideration is essential for improving the performance of brain simulation. If we view the interconnected voxels as a graph, the voxel partition problem can be modeled as a k-way graph partition problem with several constraints. The interconnection probability matrix could be regarded as a weighted directed graph G, where the vertices are voxels and edges are connections between voxels. The weight of the vertices is determined by the size of the voxels, and the weight of the edges is determined by the non-zero elements of the interconnection probability matrix. Let M be the total number of neurons simulated, Si and Di be the biological size and degree of voxel I. Then the total neuron scale in voxel I is M multiplies Si, which forms M multiplies Si multiplies Di synapses. Therefore, the traffic between two voxels, Cig, could be computed as this equation. The amount of interprocess traffic cannot be accurately estimated by a simple summation of intervoxel traffic due to message merging of the proposed communication strategy. To estimate the spike count more accurately, we use the sample function, which is denoted with the letter phi, to estimate the spike count of a pair of processes before merging, and the unique function, which is denoted with the letter psi, to remove the duplicate copies of the spikes. Since the time of each iteration depends on the process with the heaviest load, our objective is to minimize the maximum sum of traffic volume sent by each process. There are certain constraints for finding possible solutions. Firstly, the solution must divide the voxel graph into N disjoint subsets. Secondly, the scale of neurons simulated by each process is limited by the available computing and storage capacities. Therefore, the sum of voxel sizes simulated by each process cannot exceed the predefined upper bound alpha. The voxel partition problem is NP hard to find the optimal solution. To get a solution in acceptable time, we designed an effective heuristic, which we called the constraint deterministic algorithm, or the CDG. Here's the pseudocode of proposed algorithm. It begins with generating an initial solution through the chunking method. Then the algorithm adjusts the initial solution greedily so that the initial solution satisfies the size constraint. After that, compute traffic volume between processes represents with C, and traffic volume between voxel and processes represents with D. Then the algorithm iterates to optimize the solution. In each iteration, the algorithm first finds the process with the maximum outbound traffic and the process with the minimum outbound traffic. For simplicity, these two processes are indexed with I and J, respectively. After that, one of the voxels with top K outbound traffic will be chosen in Vi, and it will be moved to Vg. If the size constraint is broken, the algorithm selects a voxel which can make the size constraint of Vg satisfied again and move the voxel back to Vi. The matrices C and D need to be updated after the partition P is changed. After a preset number of iterations, the algorithm stops and returns a partition. Next are the experimental results. All of our experiments were performed in a national supercomputer. The dataset of our experiments contains the interconnection probability, size, and degree of 170,000 voxels of real human brain. The average degree of all voxels is set to be 100. The connection probability matrix is an asymmetric sparse metric with a proportion of non-zero elements of 0.06%. The communication of the simulation experiments is organized by the proposed virtual communication topology. For generality, we use VTN to abbreviate our scheme, where n is the dimension of the communication topology. In particular, when n is 1, the messages are exchanged in point-to-point manner without any optimization. That is, processes organized by weighty 1 generally use send and receive operations for communication without addressing message counts or latency cost. The baseline partitioning algorithm is constraint chunking, or CC, which divides all voxels into N uniform-sized chunks and fill the chunks in order, constrained by the sum of size for voxels simulated by each process. This figure shows how the proposed virtual communication topology affects the maximum and the average message counts. As shown in the figures, the VCT can reduce both the maximum and the average message count significantly. For example, when process scale is 800, the maximum message count is reduced from 771 to 58 by using weighty 2. It is also shown that the VCT-based communication becomes more effective in reducing message counts in larger scale systems and with higher dimension topology. When the process scale is 1,600, communication organized in a VT4 topology reduced the average message count from 656 to 21. The table shows the impact of the proposed VCT and partition algorithm on the traffic volume sent by each process during simulation. The ST columns present the maximum traffic volume of different stages and proposed VCT-based communication method. It can be seen that the VCT would not significantly increase the traffic volume, but would possibly reduce the maximum output traffic volume. For example, when process scale is 800 and partitioning the voxels through the base CC algorithm, the average and maximum traffic volume are 4.7 and 33 respectively. However, if we organize the communication with VT2, though the average count increases to 5.8, the maximum count reduces to 24.5. This table also shows the effect of the proposed CDG algorithm for balancing the communication load for all processes. When the process scale is 1,600 and communicating with point-to-point strategy, the partition using the CDG algorithm generates a maximum traffic volume of 7.8 in contrary to that of 23.4 generated by a partition obtained from the CC algorithm, which achieved a 3 times reduction. Furthermore, CDG can still reduce the maximum traffic volume by 2.4 times when combined with the virtual communication topology. In this figure, we compare the performance of the proposed method against that of the baseline algorithm with real simulation experiments on supercomputers. In the experiments shown in the figure, the communication is organized in point-to-point or 2 to 4 dimensional virtual communication topology. We can observe that both the proposed VCT and the CDG algorithm can improve the performance in actual simulation experiments, and the improvement effect increases with the simulation scale. When the process scale is 800, the communication overhead of the simulation experiment with VT2 and CDG is reduced by 31.6% compared with the overhead of the system with point-to-point communication strategy and constraint chunking partition algorithm. When the process scale is 1,600, the proposed method reduces the communication overhead by up to 41.3% comparing to the baseline method. In addition, VCT shows a better overhead reduction when partitioning the voxels via CDG. This is because the latency cost accounts for a larger proportion of the communication overhead after the traffic volume of different processes is balanced. To sum up, we tackle the communication challenges posed by large-scale brain simulations for real human brains. We designed a virtual communication topology to organize inter-process communications and proposed a merge-forward algorithm for reducing the communication overheads in brain simulations. To balance the communication loads of different processes, we formulate the voxel partitioning problem as a k-way graph partition problem and design an efficient algorithm to solve this problem. Our experiment results indicate that the proposed communication method can significantly reduce the communication overheads by up to 41% in a brain simulation with 1,600 processes. What's more, we successfully perform a human-scale simulation of 86 billion neurons and 8.6 trillion synapses with a slowdown rate of 580. Our work is part of the whole brain computing project of the Institute of Science and Technology for Brain-Inspired Intelligence. The project aims to construct a digital twin brain on supercomputers, which serves as a platform for brain scientists to explore brain mechanisms from a global perspective and explore the next generation of artificial intelligence. In the future, we will study the communication challenges of micro-column-level brain simulations and a data assimilation system capable of training the 10 trillion level parameters in the digital twin brain. That's all for the presentation. Thanks for the listening. If you have any questions, please feel free to contact me with the email address given below. Hoping to meet you soon on the online conference. Goodbye.